Imagine a stable, isolated molecule suspended in a vacuum. To understand its baseline behavior, we define its initial, unperturbed energy state using a specific quantum equation, the base Hamiltonian, denoted as H0. Now, apply a weak external magnetic field to this vacuum. In classical physics, we might treat this as a direct force pushing on the particle. In quantum mechanics, we model the field strictly as a mathematical perturbation, a small, precise change injected directly into the system's governing equations. To find the updated state of the molecule, the total energy equation becomes the sum of that original base Hamiltonian, plus this newly introduced magnetic perturbation. This addition forces the molecule's electrons to respond. Instead of yielding a single uniform reaction, the perturbation fractures the molecule's quantum mechanics into several distinct measurable effects. First, the applied field causes the original energy levels of the molecule to physically shift. Second, it induces internal electronic currents, causing charge to circulate through the molecular structure. And third, the perturbation alters the specific magnetic moments of the individual electrons. These three specific quantum-level changes combine to dictate how the entire molecule reacts to a magnet. They are the mechanical causes of macroscopic physical properties like diamagnetism and paramagnetism. To interpret complex analytical tools like NMR spectroscopy, or to engineer new magnetic materials, we have to isolate exactly how this applied field alters the momentum operator of an electron. To trace the math, we use a concept called minimal coupling. For a charged particle, the magnetic field does not enter the Hamiltonian directly as the standard magnetic field vector, B. Instead, it enters through a related mathematical construct known as the vector potential, labeled A. This equation shows the required substitution. The standard momentum operator of the electron, p hat, must be systematically replaced with the sum of the original operator and the product of the electron's charge and the vector potential. The Hamiltonian requires us to square this new perturbed momentum operator. Expanding the binomial yields a specific three-part algebraic result. Looking at the expanded result, the first term, p hat squared, is simply the original, unperturbed kinetic energy of the electron. The middle component contains the vector potential A to the first power. We call this the linear term. Because it scales linearly with the applied field, this term mathematically governs how the external field interacts with the electron's angular momentum and spin. This is the primary origin of paramagnetic behavior. The final piece of the expansion features the vector potential squared. This is the quadratic term. This second-order term represents the tendency of an electron cloud to develop induced currents that physically oppose the external magnetic field. It serves as the mechanical origin for diamagnetism. A single substitution and expansion splits the molecular magnetic response into two distinct mathematical phenomena. Diamagnetism and paramagnetism originate from entirely different sections of the perturbed equation. The perturbation equations also dictate the physical flow of charge through the molecule, a property called current density. Total current density, represented by the vector J, is the required sum of two distinct flows, the paramagnetic current and the diamagnetic current. This introduces a strict mathematical condition. Consider a stable molecule at rest, with paired electrons and zero external magnetic field. Under these conditions, the molecule's wave function is entirely real. According to the formula, calculating the paramagnetic current requires finding the difference between the wave function and its complex conjugate through these gradient operations. If the initial wave function is completely real, it is identical to its complex conjugate. Plugging identical values into this subtraction results in a perfect mathematical cancellation. The paramagnetic current is exactly zero. To generate a current, we must apply the external magnetic perturbation. This action directly forces the previously real wave function to become complex, breaking the symmetry of the equation. This shift to a complex wave function permits a direct interaction with the external vector potential, resulting in the immediate generation of diamagnetic current. Because closed-shell organic molecules begin with completely real wave functions, they lack any stationary paramagnetic current. When exposed to a field, the math dictates that their primary reaction will be the induced opposing flow of diamagnetism. The rules change for exceptions like open shell molecules, free radicals, or systems possessing orbital degeneracy, such as oxygen gas. To map out the paramagnetic susceptibility of these molecules, physicists use a perturbation formula known as the sum over states equation. The denominator of this summation represents the specific energy gap between the molecule's stable ground state and an available excited state. The numerator calculates the strength of the interaction, how aggressively the ground state and the excited state mix together under the influence of the angular momentum operator. When an excited state is close in energy and strongly connected by this operator, the mixing is intense. This generates a paramagnetic current density, a flow of charge that actively aligns with and reinforces the applied magnetic field. Diamagnetism is an immediate, reactive response to a vector potential. Strong paramagnetism is strictly dependent on the proximity and quantum accessibility of low-lying excited states to facilitate that orbital mixing. Translating these theoretical models into applied computational chemistry introduces a severe technical hurdle known as the gauge problem. The perturbed Hamiltonian relies on the vector potential A rather than the physical magnetic field itself. The mathematical flaw is that the vector potential is not unique. You can apply a gauge transformation, adding the gradient of any smooth scalar function, and still yield the exact same physical magnetic field. In pure, exact quantum mechanics, physical observables remain completely gauge invariant. The equations self-correct. But real-world molecular modeling relies on mathematical approximations. If an approximate calculation is run using an arbitrary gauge, the resulting predictions for current density or energy shifting might shift depending on the chosen origin point. This is a violation of physics. To extract valid predictions, modern computational chemists employ advanced algorithms, specifically gauge-including atomic orbitals, to ensure structural models remain physically accurate regardless of the mathematical gauge chosen. By applying these perturbation rules, we can predict exactly how specific molecular structures will register on macroscopic analytical equipment. Take the classic model of a benzene ring, defined by its delocalized cloud of pi electrons. Applying a magnetic field directly perpendicular to this ring triggers the quadratic term of the perturbed Hamiltonian we mapped earlier. This specific second-order term forces those delocalized electrons into a continuous circulating flow around the carbon framework, creating a diatropic ring current. As this charge circulates, it generates its own localized magnetic fields. These internal fields physically oppose the external magnet near the center of the ring, but reinforce it at the perimeter where the hydrogen atoms sit. This precise local variation in magnetic shielding dictates exactly where the resonance frequency of the hydrogen atoms will occur. This is the mechanism behind chemical shifts plotted on an NMR spectrum. If we replace the benzene ring with an open shell radical, the physical output completely changes. For a radical, the applied field interacts with the unpaired electron. The linear term of the Hamiltonian dolonates the response, acting on that unpaired spin to physically split the molecule's energy levels. By firing microwave radiation at the sample, we induce transitions between those split states. This is the underlying mechanism of electron paramagnetic resonance spectroscopy. From determining the structure of a novel organic compound to capturing an image of human tissue inside an MRI, macroscopic magnetic phenomena operate on exactly the same principle. They are the direct, measurable results of a perturbed quantum Hamiltonian.